In the grand theater of the cosmos, few ideas are as captivating as the wormhole, a theoretical shortcut through the very fabric of space and time. Born from the mathematics of Albert Einstein's general relativity, a wormhole is an Einstein-Rosen bridge, a tunnel connecting two distant points. Imagine folding a map so that your starting point and destination touch, then punching a hole through them. That's the idea. If they exist, we'd likely find these cosmic doorways in the most extreme environments imaginable, with the crushing heart of a black hole serving as a potential entrance. But there's a critical catch. Any natural wormhole would be catastrophically unstable, collapsing in on itself faster than light could pass through. It's a door that slams shut the instant it opens. To hold it open, we would need something straight out of science fiction. Exotic matter, a hypothetical substance with anti-gravity properties that could theoretically prop the tunnel open long enough for safe passage. And if we could build one, could we travel in time? Theoretically, yes. Here's how. Imagine creating a stable wormhole. You'd leave one mouth stationary, perhaps near Earth, and send the other on a journey at nearly the speed of light. Because of an effect called time dilation, time would pass much slower for the traveling mouth. When you bring it back, the two ends would be connected to the same location, but separated by years, or even decades. You would have a bridge connecting not just two places, but two different moments in time. Step into the younger mouth, and you'd emerge from the older one, arriving in your own past. Of course, this raises mind-bending paradoxes. Could you change history? Or would you simply create a new, parallel timeline? For now, wormholes remain on the far edge of physics. They are not something we have seen, but a profound what-if, born from our deepest equations, a tantalizing dream of a universe where the rules of distance and time might just be breakable. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna in New Jersey. But they were plagued by a persistent, annoying hiss, a cosmic static they couldn't eliminate. They aimed their antenna at different parts of the sky. They checked their equipment. They even cleaned out the pigeon droppings inside the horn. But the faint, uniform noise remained. It seemed to be coming from everywhere at once. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists was building a detector to search for the very thing they had accidentally found. It was the echo of creation itself. That persistent hiss wasn't noise. It was the oldest light in the universe, the afterglow of the Big Bang. We call it the cosmic microwave background, or CMB. Think of it as the baby picture of our universe. In its first moments, the cosmos was an incredibly hot, dense soup of particles and energy. Light was constantly bouncing off charged particles, unable to travel freely. But after 380,000 years, the universe expanded and cooled enough for atoms to form. Suddenly, the light was set free, and it has been traveling across the cosmos ever since, stretched by the expansion of space into the faint microwave glow we detect today. At first, this glow seemed perfectly uniform. But when our instruments became sensitive enough, they revealed a stunning, mottled pattern of tiny temperature differences, ripples that are only 1 part in 100,000. These ripples are the cosmic seeds from which all galaxies and galaxy clusters would eventually grow. And it's here, in these tiny ripples, that we find one of the most powerful pieces of evidence for dark matter. In the early universe, two forces were at war. Gravity was pulling matter together, trying to form clumps. At the same time, the intense radiation pressure of the hot universe was pushing it apart. For ordinary matter, the stuff that makes up stars, planets, and us, this created a sloshing effect, preventing it from clumping together too quickly. But dark matter is different. It feels the pull of gravity, but it doesn't interact with light at all. So while ordinary matter was being pushed and pulled by radiation, dark matter could quietly begin to clump together, unimpeded. It formed vast, invisible gravitational wells, a cosmic scaffolding waiting for the rest of the universe to catch up. When the universe finally cooled and the CMB was released, ordinary matter was free to fall into these pre-made gravitational blueprints, laid down by the dark matter. The size, spacing, and intensity of the hot and cold spots we see in the CMB today are a perfect match for a universe where this invisible scaffolding gave ordinary matter a massive head start. Without the gravitational influence of dark matter in that first 380,000 years, the structures we see today simply wouldn't have had enough time to form. The baby picture of our universe isn't just a picture of light, it's a map of the invisible dark matter that shaped it.